Okay, good morning. So we are going to go over the practice quiz number 4. So these are the problem that you are going to get 6 questions from. It's mainly line integrals, okay, line integrals, and end up with the Green's theorem. And there is no example of the Green's theorem on this practice one. Then I'm going to give you a couple of them. So one question on the Greens, and then the leftover is going to be surface integral. So 6 questions from this quiz would be repeated again for the final. So when we review the final, we just there are going to be 2 more problems from the surface integral that we started the other day. Okay, so I'm going to do the problems, and I will add 1 more to it, and that would be related to the Green's theorem. Okay, so let's go back to my lecture notes. So we give you I will post the quiz later tonight or tomorrow morning. Then on Monday, I finish the leftover on the leftover or the surface integral, and you already got all the solution for the final review. But on Tuesday, I just do the part with the surface integral and explain a couple of problems on the quiz. But otherwise, the rest are the one that you already got them. Okay. And first, I have to grade your test 3. So this is it. We are going to check the practice. Thursday. So be careful about this quiz, okay, and study the problems because you are going to see them again at the end of the week when we get to the final similar questions. So this is mostly line integral. So this is practice quiz number 4. The first part is the warm-up, if you like, because as you saw it, we are very much interested in the conservative. We talk about the vector fields, and we are going to be interested in vector fields that are conservative. When they are conservative, then there is going to be a potential function, because that's a part that we use in order to find the line integral. So we give you one of them, or you are going to do it automatically in 2 of those problems. So there you are. And the first question is going to be determine if the vector field is conservative. Okay, determine whether or not the vector field, the vector field is conservative. If so, you have to find the potential function. Okay, if so, find its potential is a potential function. You know that you are going to find the function, okay, whose gradient is the same as the field that you are dealing with. Okay, so we're taking the part 1. So the function can be function of 2 variables or 3 variables. 3 variables takes a little bit more time, but nothing to worry about. Okay, so the first one, the function is f of x, y, z is equal to y squared z cubed plus cosine of x. That's the first component. The second component is going to be, so it's a plus 12x y z cubed, okay, minus e to the negative y times j. So this is going to be your second component. And the third component is a 3x y squared z squared minus 1 equal to the k. Okay, so it's a function of 3 variables. So quickly we can test to see if this is a potential. It's very easy to test. Remember the component function, we call it MNP. M and P. Then to see if the potential function, you compare them together. See, the comparison are going to be, this is it, you compare the M with the M and the P. So this is the way we are going to compare it. Okay, so this is M. So what we're going to do is, this is going to be the partial of the, if you want to compare the M with the N, M is in the first position, this is the second position. So I find the partial of the M in respect to the Y. Okay, M respect to the Y. So that give me 2y z cubed. Then I want to compare it with this one. So I take the N is in the position of the Y, so compare it with the M, so I take the X. Okay, round N and round X. So this is it, that's going to be Mn. So differentiate with respect to the X. If there's respect to the X, that simply give you, okay. So if I do this one, this is going to be the, this is I have to differentiate respect to the X, yes? Differentiate respect to the X, that give me 12X, 12X. I just want to make sure I didn't miss anything over here. So let me just check. So that was a y squared z cubed plus the cosine X. Okay. So this is a 2y z cubed. Then I get the N. This is going to be the N. Oh, sorry, that's a 12. I didn't see it. That's a 12. Okay, this is going to be respect to the X. That gave me 12y z cubed. This is going to be, sorry, this is 2 only, not 12. Okay, that's why I was just looking for it. So that's it. Okay, that's a 2xyz cubed. So as you can see, both of them are the same. So I got the first one. Okay, then I'm going to compare the M with the P. So I find the round of the P. So I want to round off the px with respect to the x, that give you 3y squared and the z squared. I compare it with the m, so I have to find round m, round z. Round m, round z, that give me the same thing, 3y squared, z squared. So I got it, round m, round z is equal to the round p, round x. Okay, this is going to be the case. The leftover is I'm going to compare these two together, n and the p. So I find what is round n, round z. Round z give me 3 times 2, 6, 6 x y z squared. And I find the round p, round y. Round p, round y, that give me the same thing, 6x y z squared. So it's true. You can go ahead and find the potential function. If you can find the potential function, this means they are going to be, okay, I just did this one so that you can see it. But you can go for the potential function. If you can find the potential function, this means automatically that your force is going to be conservative, but you better check it first. Okay, so the conclusion is going to be this force, F is conservative. So the next step is find the potential function. So the potential function is going to be, suppose F is its potential function, and this is it. So you are going to have the gradient of the F is equal to the F. So you are going to find a function to satisfy this condition. Okay, satisfy this condition, and you know this is it. So we're going to let the partial of the x, partial respect to the y, partial respect to the z, to be equal to your function. The function is M, N, P. You let them be equal to each other. You have a system of three equations, three variables. Then you are going to be able to solve it. Okay, so I go to the next page. I'm going to check these and let them to be equal to each other. I have the M and P, and it takes a little bit time, but you have to do it at least on the once in this quiz and once on the final. Okay, so be patient and practice. So there you are. This is a system that we're going to have. So the partial respect to the x equal to the m. Okay, the m is y squared. Y squared is z cubed plus cosine of x. That's the first part. Partial respect to the y is equal to the n. N is 2xy z. Okay, 2xy z cubed minus e to the negative y. Partial respect to the z is equal to the p. And the p is 3x y squared z squared minus 1. Okay, so this is the system that we have to work with. The function, we call it 1, 2, 3. You integrate one of them, then you are going to have a constant, which may depend on the other variables. You have to talk about it, okay? So all of them are the same. Let's start with this one. Start with number 1, integrate respect to the x to find your function. So this is it. So the function f of x, y, z. Okay, f of x, y, z is going to be integrating respect to the x. So it's going to be y squared z cubed plus cosine x, integrating respect to the x. If you integrate respect to the x, that gives you x y squared z cubed. Integral of a cosine would be sine, but you may have a constant. But your constant can be a function of y and z. So we call it g of yz. Okay, so this is going to be the first part. So far, this is going to be your function f, but the question is going to be what is g of y and z? So you have to differentiate respect to the y to test it, to see if it's going to be any y in it. Okay, so there you are, differentiating respect to the y is going to be equal to differential respect to the y, so that gives you y squared with 2y, so 2xy z cubed. Okay, z cubed, this would be 0, and that would be derivative of the g respect to the y. Okay, so at the same time, you can bring this one from number 2. So from number 2, you have the f sub y derivative is going to be 2x y z cubed minus e to the negative y. So you compare them together, these two would cancel out. Then the conclusion is going to be round g round y is equal to the negative e to the negative y. Okay, now we integrate it to get the g. If you're integrating respect to the, okay, if integrating respect to the y, so what's going to be the result? So from here, g of x y, you know that the integral of negative e to the negative y would just e to the negative y. But you may have a constant, but your constant can be a function of z. So we're going to call it h of z. Okay. So this is going to be the the case. So if you put it back, your function is going to be so far. So the function is f of x, y, z. So far it's x, y squared, z cubed plus sine x. And then you have e to the negative y plus h of z so far. But you have to check to see if there is any z in it. So in order to do it, you have to go with the third part. So differentiate respect to the z. So find f sub z. Derivative of z cubed would be 3z squared. So it's going to be 3x y squared z squared. This would be 0, 0. We get h prime of z only. So compare it with the h of f of z from number identity number 3. So f sub z is going to be 3x y squared z squared minus 1. So if you compare them together, so these two would cancel out, we get h prime of z equal to the negative 1. So the conclusion is that the h of z integrated, that give you negative z plus the constant c that you don't need it. Okay, so we're going to add the negative z here, and that give you a potential function. Okay, so f of x, y, z is equal to the x, y squared, z cubed, plus the sine x, okay, sine x plus e to the negative y minus the constant c, if you like the constant. You don't need the constant c really. So that gives you the potential function. Okay, so get to know it because you have to do it at least once. Later on, you know, when you want to integrate a function of, there's going to be a line integral through a function of 3 variables. So that give you the case. Okay, so that's going to be the first one. Any question? So the 3 variables takes time, but the 2 variables are going to be easier to handle. Okay, let's quickly check one of those 2 because we need most of the time the 2. Okay, that was the 1a. So the question on the second function is 1b. The 1b, the function is a function of 2 variables. So that's a field. You have a vector field in R2. And the situation is this one. The function is given to you as it's a 2x cosine square of y. And 2, just double check this one. Okay. Make sure to get the one that I gave you. So the 2x cosine square of y, and the second part is 2y. 2y minus x squared. Okay, minus 2x squared sine of the 2y. So that is your second function. Okay, it's a field. It is a scalar field. It's a vector field, but in R2. Okay, you know that you are going to call this one M and this is N. So you compare them together, that's the X and the Y. So you compare the round M around the Y. You compare it with the other side. So that's it. Differentiate respect to the Y. Cosine squared is going to be -2, that's going to be -4 X cosine of the Y times the derivative sine of the Y. Okay, that's the first part. Okay, you want to compare it with the other one, so it's going to be round N around X. You see, when you differentiate respect to you switch the place. That's the first component, the X, second component Y. Okay, derivative respect to the X, this would be out, and you don't have to use the product. Derivative of negative X squared would be just simply negative 2. Okay, so that gives me negative 2x. Okay, so that gives you a negative 2x, and now derive the sine of the just differentiated respect to the x. So this would be 0. Okay, this would be 0, and this is going to be negative 2x sine of the. I don't see this one because I'm going to differentiate respect to the x. I have to check it again. So the first part was 2x cosine square of the y. So when I differentiate it, that is going to be the case. Okay, so the second part is negative 2x. Let me see what is wrong with this argument. Probably something. It is not going to be. What I'm missing is. Sorry about that. I have to check it. Because when you differentiate it, that give you. Okay. There is something nice about it. It's going to be negative 2x as sine of the 2y. Okay, sine of the 2y, and just compare them together. You know that the sine of the 2y is 2 sine 2 cosine. Okay, that's going to be the one. So it's a negative 2x. Interesting. So that gives a negative 2 sine y cosine y. Okay, so you know it's the same. That's going to be negative 4x sine of y cosine of y. Okay, so they are equal to each other. So they are going to be equal to each other. And because I knew that this must be conservative force. Okay, any question? So this is a sine of the 2y, 2 times y, not sine square. 2 times y, they are going to be the same, you know that. You can check this one, sine of the 2y, double angle. Sine of the double angle is going to be twice of the sine of the y times cosine of the y, 2 times 2, 4, so it's correct. So this means F is a potential. Okay, I was surprised because this must be, F is conservative. Okay, F is conservative. Okay, so the question is going to be, again, suppose we're looking for the potential function. Suppose F is its potential function. Okay, so you let them equal to each other. The gradient of the F must be equal to the F. It's just a function in R2. So this is going to be partial of the F respect to the X, respect to the Y. And this is going to be your Mn. So you are going to forming a system of 2 equations, 2 variables. Okay, 2 equations. This is it, F sub X equal to the M. So your M is 2x cosine square of the Y, and F sub Y equal to the N. So your N is 2y minus x squared sine of the 2y. So that would be your equation number 1 and 2. Okay, it's a kind of system of the partial differential equation that you want to solve. Again, you start with one of them, and it's easy to start with the first one. You integrate respect to the x to get the function back. So we're starting from the 1, and then we integrating respect to the x. It's a 2x cosine square of the y dx. Easy to integrate is a 2x integral of 2x squared over 2, which is x squared. So that gives you x squared cosine square of the y. There is going to be a constant, that be a constant of the function of y. So we have to check the gy. So we have to differentiate respect to the y and then compare it with the second part. So differentiate respect to the y. Respect to the y, we have it again that cosine squared, which is going to be negative 2 cosine times, so it's going to be negative 2x squared. Okay, cosine of y times the sine of y, which is the same as that sine of 2y that we talk about it. So you compare it with the part 2. So you compare it with this one. So if you compare these two together, okay, so we go with the 2, and we find that the f sub y is going to be 2y minus x squared sine of the 2y. These are going to be the same. See, because 2 sine cosine would be the sine of the 2y, and it's going to be the same. If you like, I can write it down here that this is the same thing as I did it on the top. So these two would cancel out. So the leftover is going to be, okay, I differentiate respect to the y, and there is going to be a g prime of y here, of course. There is a g prime of y here because we differentiate respect to the y. Now, when we compare them together, the conclusion is that the g prime of y is going to be 2y. Okay, any question? I differentiate this one, so I missed the g prime of y. So there is a g prime of y here too. So g of y, you integrate that, give y squared. Okay, you can have y squared, or you can y squared plus c. We are going to be interested in just one of them. Okay, so that's easy. Just go back and substitute here to get your function. So the potential function f of x comma y is equal to x squared cosine square of y plus y squared. That would be enough, but y squared plus c is going to be the actual angle, actual, solution. Okay, so you receive one of them in the quiz. So that's how you take it when it's a function of two variables, or it's going to be your vector field is going to be in R2 on the plane. Any question? So I'm checking the third one. So there is a misprint so that we can see what is the actual problem is. So the third function, that's a 1c. The function must be in this form. This is the question. You want to check if this is going to be a conservative field. So it's a vector notation. It's going to be x ln of y. That's the first component, and the second component is negative x y. This is the actual question. Okay, so we are going to check it. It's R2, so this is m and n. So we just compare the m and n together. Okay, there you are, derivative respect to the y, the other way around. M respect to the y. With respect to the y, x would be fixed. The derivative of ln y is 1 over y. So this gives you x over y. Okay. And differentiate n respect to the x. Derivative of x is just 1. So that gives you negative 1 over y. As you can see, they are not equal to each other. Okay, that's it. It's not. So round m, round y is not equal to the round n, round x. So f is not conservative. So no further action is needed. Okay, so that's it. That's our first concept, if you like. Whether it's going to be potential, if there is going to be a potential function. Now, then line integral. We'd like to find the line integral for us. We are going to give you kind of 3 types of the integral that you have to find for us. The first one is ordinary, nothing special about it. We give you a function, we give you a domain, and then you are going to find it, okay? The second one is going to be the one that we are going to discuss whether that integral would be independent of the path. We may ask you to prove that it's independent of the path. You know that when it's independent of the path, if f is conservative, then the integral is independent of the paths. And if it's going to be the case, then you can find the integral using the fundamental theorem of integral for the line integral, which is simply the integral is going to be just like the antiderivative that we did before. If it's going to be conservative, you find the potential function, and the result of your integral is going to be evaluation of the potential function at the endpoints. This is going to be the second one. The third one is the one that you can use the Green's theorem to find it. Okay, so 3 questions on the integral for this quiz, and the 3 for the final. So we start with the first one. This is number 2. The first one, very standard. We would like to find the line integral on a triangle. Triangle is a very good case for the graph, okay, for the curve or for the domain. So get to know it. So what we'd like to do is this one. That's the first type of the line integral that you are going to have. Evaluate the line integral. Okay, the line integral. So you do this one 3 times, but this time, this is it, the line integral on the C. And you know that the notation going to be x plus y. This is going to be differential of the arc length, lowercase s for this group. Okay, this is going to be the case where you have to give us an address. Where is C? C is the path. C is going to be the triangle. Okay, is going to be a triangular, if you like. Is going to be triangular region going around the triangle, okay, with the vertices. It may be a square, it may be a circle, or it may be, okay, a triangle. With these vertices, we give easy vertices to be able to parameterize it quickly. So it's going to be 0, 0, okay, 1, 0, 1, 0, and 0, 1, 0, 1. Okay, this is it. There's nothing extra about this one. It must be done directly. Okay, so the situation are going to be, so this is going to be the solution. So identify the path that you have to identify what type of curve do you have or are going to handle it. So get the triangle. This is going to be a triangle that we have. So where is the point? You have a 0, 0. This is 0, 0. Okay, start with the 0. Then you go to the 1, 0. So this is going to be 1, 0. Then you go to the, okay, 0, 1, 0, 1. So this is going to be your triangle. Okay, this is going to be a triangle. So you have to create the path C. Okay, a path and the direction is counterclockwise. Okay, so this is going to be the C. You start from here, then here, then you come back. It's a closed path, but this is not the type that be able to do those. If you apply any theorem, it's a direct substitution. Okay, so you identify your curve. You see, you have to divide it into different parts. So your C would start from this part, this segment, you may call it C1. This segment, you can call it C2. And this segment, you can call it C3. Okay. So you realize that your paths are going to be 3 paths, going to be C1 plus C2 plus C3. So you have to break your integral in those 3 paths. So you better have the parametric equation of each paths right away. These are easy to find, okay? For example, if you want to find this one, you see x increasing from 0 to 1, and the y is constant. So if you want to identify the C1, so the C1 curve is, so we get the x is going to be equal to the t, okay, because it's changing. Y is fixed, is equal to the 0. Then you have to pick the t so that they give you the initial point and the terminal points. So we get the t between 0 and 1. If you put t equal to the 0, that gives you 0, 0, which is a 0, 0. If you put t equal to 1, that gives you 1 and, okay, 1 and 0. So that would be C1. Any question? They are not difficult so that you be going to the formulas. And the formula is going to be initial point 0, 0, terminal point 1, 1. You can write the equation of the line. You know that. It's going to be initial point plus t times the terminal points. Okay, it can be done when it's complicated, but not for this one. So let's go with the C2. So what happened with the C2? This is going to be the C2. You can write the equation of the line if you like. The line is going to be 0, 1 going to the 1, 1. One way to do it is this one. The other one is just look at what would happen to the x and the y. You see, when we go to this direction, x would be decreases from 1 to 0. That's going to be for your x, but your y would be increasing from 0 to 2 to t. So one way to do it is, this is x. This x would be decreases, we'll write 1 minus t. This is going to be for x. Your y is increasing, you may call it t. Then you have to pick the t between, so that you get those 2 points, it's going to be 0, between 0 and 1. If you put t equal to the 0, that give you 1, 1. Okay, put t equal to 0, you start with the 1, 1, 0. This is 1, 0. And if you put t equal to 1, that give you 0, 1. That give you 0, 1. Okay, so it's not a big deal really. See, the equation is, if you like, the initial point is here 1, 0. You see, this is going to be your initial point. Then it's going to be plus t times the terminal points. So the terminal points over here is going to be what? So you have 2 points, 0, 1. Okay, 0, 1. That take you to the 1 and 0. So the other way around, I'm sorry. That's a 1, 0. 1, 0 take you to the, okay, take you to 0, 1. So your initial was going 1 and 0. The t, you see, if you consider the difference between these, the difference that you're going to have, that give you 0 minus 1, and that give you 1. So this is going to be 1, 0 plus t times negative 1 and 1. So if you put them together, you will see that it's going to be, you end up with 1 minus t, 1 minus t, and the t. So this is going to be your x, and this is going to be your y. You see x equal to the 1 minus t, and y equal to the t. Okay, you know, in case you missed it, or you want to check it, or it's going to be more complicated on this step, maybe find it. Any question? So that would be C2. And the C3, the same story, but it's easier to find. C3. In the C3, what you have over here, x is constant. You see x is 0 because you are on the vertical line. So x is equal to the 0, and your y is dropping down, y from 1 to 0. When it's dropping down, you call it again 1 minus t. Then you check the t between 0 and 1 and make sure you get it right. If you put t equal to the 0, that gives you 0, 1. That's your initial point. And then when you put equal to 1, so that gives you 0, 0, you end up here. Okay, everything must be consistent. Any question? So you have to parameterize this type of region. So now you know that your integral is going to be integral of the function. You want to find the x plus y ds over c. So you have to divide it into 3 parts. Okay, so divide it into you over the c1, over the c2, and over the c3, and you know the formula for all of them. It's going to be what? For all of them, you are going to have the integral of f of rt. Remember, f of rt times it by norm of the r prime of t, then the dt. This is the formula that you're going to find there. So these are going to be your function. Then you drop the r of t, then you find it in each group, and you are going to get it. Okay, any questions? So I'm going to do it quickly. You have to do it for the C1, C2, C3. You find them, and then you add them together, and then you're done. So I do one of them quickly. So I'll be working with the C1. Okay, you're working with the C1. The equation of a curve RT is going to be your x was t, y was 0. So this gives you t and 0. You find the r prime of t. Okay, so your r prime of t is going to be 1 and 0. Then you're going to find the norm of the r prime of t. Norm of the r prime of t is going to be radical 1. You know that the square root of the square of this component. So it's going to be radical 1, which is 1. So that would be the r. Any question? So the integral. And the integral of x plus y ds over c1 would be changed into the, you substitute x and the y from the function, okay, from the r of t, x is equal to the t and y is 0. So that gives you t plus 0. T plus 0, the leftover is going to be norm of the r prime, which is equal to 1. Okay, it's going to be equal to the 1 and the dt, and the t going from 0 to 1. Okay, so basically you're integrating 0 to 1 t dt, which is going to be 1/2 of the t squared going from 0 to 1. Okay, then you substitute. So the result would be 1/2. So this is integral of the first part. Any question? So the formula is f of r of t norm of the r prime of t dt for the scalar valued function. Okay, we do the same thing with the C2. So for the C2, r of t is equal to, the function is going to be 1 minus t, 1 minus t, and t. So you find the r prime of t. So r prime of t is going to be -1 and 1. And you get the norm of the r prime is going to be a square root of 1 plus 1. That give you 2. So radical square of the component. So that give you radical 2. Okay, so it's going to be radical 2. Just come back and get the integral x plus y ds or ct, so c2. So that gives you 0, 1. Substitute, x is 1 minus t, y is t. So it's going to be 1 minus t plus t. Then the norm of the r prime of t, which is radical 2, times the dt. Okay, this t and t would cancel out the negative t. So simply you are going to integrate 0 to 1 radical 2t, which is equal to the radical 2t from 0 to 1. So that gives you radical 2. So the integral of the second one is radical 2. Any question? So the C1, C2. So we got to do the C3. C3. In C3, your function was x was 0, y was 1 minus t. So r of t is going to be equal to, okay, r of t is equal to the, that's it, we get 0 and 1 minus t. That is going to be the case. So r prime of t is going to be 0 and -1. So the norm of the r prime of t is going to be equal to the 1 again. Okay, that gives you 1 again. Then we get the C3. Okay, so what's going to be the integral over the C3? So you get an x plus y ds over the C3. X plus y, your x is 0 and the y is 1 minus t times norm of the r prime of t, which is equal to 1, and the dt from 0 to 1. Okay, easy integral to apply. So it's going to be 0 to 1, 1 minus t dt. Okay, then you integrate it. So that gives it t minus t squared over 2 from 0 to 1. And so that gives you 1 minus 1/2, which is equal to the 1/2. There you are. So the conclusion, the integral of x plus y ds over the c is equal to, over the c1 we get the 1/2, over the c2 we get radical 2, and over C3, you get 1/2 again. So 1/2 and 1/2 would be 1, so that give 1 plus radical 2. So the integral of x plus y ds or along the C is going to be equal to the 1 plus radical 2, and we are done. Okay, so we've got to be patient. So at least one of them. The others, you connect it to the theorems and it can be done quickly, but no big deal. We can do it. That is going to be. So that is kind of the line integral. Everything is classic, general, and the way we are going to do it. Okay, that's a type 1 of those integration they're going to be interested in. Any question? Type 2, this function was a function of 2 variables. We are going to give a function of 3 variables, okay? But the format is going to be integral of now p dx, q dy dz. It's a strict substitution, really. It's not a big deal, but you have to do this strict substitution. On Monday, we are going to see the Stokes theorem. And one way to evaluate the integral in the Stokes theorem is of this category, okay? But there is a theorem for it. But for the Stokes theorem, we give you something to verify. So this means you have to find the quantity to the right and to the left of the equation, sides of the equation, let them to equal to each other. That's why you need this type of argument. Okay, so this would be number 3. And again, evaluation of integral directly, and nothing involved, nothing special. So this is it. You're all straightforward. So we want to evaluate this line integral for the function of 3 variables. The line integral okay, the line integral is the one that we want to find. Is of this form, is or along the C, but the form is differential form, if you like, e to the x dx. They call it differential form. E to the y dy plus e to the z dc. This is it. And C is going to be a curve. C is a curve, smooth curve, with the parametric equation. With the equation is given to you directly. Okay, and the equation is a t squared, t squared t cubed, and when t is between 0 and 1. This is a straightforward problem. It's just a direct substitution because it's in differential form. So you have to change this onto the x, y, z. So your x is t, your y is t squared, and your z is t cubed, and directly substitute. When you substitute, everything would be end up with a function of t, and all those differential would be dt, and you can find it. Okay, this is, we call it the direction, the direct substitution, or just the method. Okay, so this is it, solution. So quickly get those results that you have. You have the equation of the curve, because remember it's f of r of t, so you have to plug in the r of t. So it's going to be t squared t cubed. Okay, and you imagine of this one as x, y, z. So this means your x is equal to t. So your y is equal to the t squared, and your z is equal to the t cubed. Since you're working with the differential, so you have to find the differential of each one too. So that gives you dx is equal to the dt, dy is equal to the 2t dt, and the dz is equal to the 3t squared dt. That's it. Go back directly, substitute here. Okay, so the given integral, it's a e to the x dx plus e to the y dy plus e to the z dz, e to the z dz over c. Substitute is going to be equal to e to the x. What is x? X is t. Times that by dx. dx is dt, that. Plus e to the y. What is y? T squared. Times that by dy. dy is 2t dt. Nice for the integration. Plus e to the z. Z is t cubed. T cubed times the dz, 3t squared dt. You see? Nicely, all the differential are available. So we can integrate it right away. Of course, this is going to be integral. Your t is between 0 and 1. 0, 1. Okay, directly integrated, the integral of e to the t is just e to the t. You see, the first one, this is e to the t squared. If you call u to be t squared, du is 2t dt. So this integral is simply e to the t squared, because u prime is available. And this is e to the t cubed. If you take the u to be t cubed, du would be 3t squared dt. So this would be just e to the t cubed. That's it, from 0 to 1. Substitute. If you put the t equal to the 1, that gives you e minus. If you substitute 0, e to the 0 for all of them would be 1. So we get a 1, 1, 1. So the result is simply 3e minus 3. That's it. So the integral would be 3e minus 3, and with that. Okay, we just wanted to get yourself familiar with the different version of these integrations. So everything is given, directly we substitute, and then it's just we end up with the integral respect to the t. Okay, so that's a type 2. Any question? Now the interesting one is the type 3. We are going to give you a line integral, and we want to find it. We want to find it. Okay, but your curve is going to be a curve between 2 points, but it is not going to be a special curve. We wanted to do it for any possible curves. Okay, any, not a fixed one. This is where you have to use some theorems. Okay, so these are direct substitution, but not this one. Interesting one is this, number 4. So you have to recognize it yourself. So what we want, so we want to evaluate the line integral. Okay, evaluate the line integral. Line integral. And this is the line integral. You have integral of 2x, okay, xyz, 2xyz dx, just a differential form that we have, plus the x squared z dy, okay, and the plus x squared y dz over the c. Okay, it's like the previous one that you did. For the previous one, you did have your equation of the c. But in this case, look at this one. When c is what? Is any curve. Any. Is any curve. Okay, is going to be any curve, any path. Okay, between the points. Between 2 given points. Between the points. Okay, the points are, we call it A and B. This is going to be 1, 1, 1. And the other one is going to be 1, 2, 4. You see, it's any. So not for the specific one. Okay, so this is situated. You see, this is A, this is B. So this may be C. This can be C, or this can be C. Okay, you don't have any specific C. So in this one, what you have to do is, so this means, you see, since you don't have the C, a specific C, so what you have to prove first is to prove that this integral is independent of the path. Independent of the paths means I can do it for any, if you change the paths, but you keep the initial point and the terminal point to be the same, the value of this integral never changed. How are we going to do it? In order to do it, you know that the function involved must be a potential function. So if you get a function, the potential function, that this is going to be your, okay, these are going to be your component, you know, you can call it MP, N. If it is going to be, for example, the M, and this is going to be the N, and this is going to be the R that we usually call it, okay? If this is going to be the case, then you are going to form a function. You're going to form a vector field. So if you prove that the vector field is going to be conservative, then automatically you are free to use any C you like. Since any C you like, you pick the, you know, it doesn't matter whatever you pick, because your conservative field, you see this is going to be your F, so you find the potential function. As soon as you get a potential function, so this integral simply, the integral would be the value of the potential function at the, okay, at the terminal points. Since these graphs are optional, so you pick what? You pick a straight line. If it's going to be a straight line, so in that case, R of B would be just the evaluation of the function at the terminal points minus the evaluation of this function at the initial points, and then you're done. Okay, so this is how you set up these type of problems, because you don't have a specific C, so you have to prove that this integral is independent of the paths. So you have to prove that the F is conservative. As soon as you put F is conservative, everything else would be follows. So you are not going to integrate really for this type of functions. Okay, then you prove it. Any question? So this is a very important problem, and you have several of these problems in your book, and you can check if you need more. Okay, so this is going to be the plan. The plan is clear. So what we're going to do is we are going to start the introduce the function, the vector field. So you pick those to be component of your vector field. Suppose f of x, y, z is going to be the first component 2x, y, z. Okay, the second one x squared z, and then x squared y. This is going to be your function. Okay, so you assume that you're not going to check it whether it is conservative or not, because eventually you want the f. So you suppose this is, suppose this is, okay, is conservative, and f is its potential function. So you can start with the gradient of the f equal to the f and continue. Okay, so you predict that there is a function, okay, it is conservative. Then if you cannot find this function, automatically you find out. But the way they worded the problem, that will tell you that probably this is a conservative force. Okay, so there you are. You have to go over that method again. F sub x, F sub y, F sub z. So this is going to be your M, N, P, or R, whatever. It doesn't matter. Component. So that three system of the equation, F sub x equal to the first component, which is a 2x, y, z. F sub y. It's usually not a complicated function. It can be done quickly. X squared z. Then we get the F sub z, which is going to be x squared y. Okay, this is going to be our system of a partial Okay, partial derivatives or partial equations. Okay, go for it. It's not a difficult function to handle. So start integrating the first one, for example, to start with. Okay, so what I'm going to do is start with the first one. So I have the function. If I integrate this one respect to the x, 2x, y, z, dx. So 2x, integral of 2x would be x squared. So that give me x squared yz, but the constant g of yz. So this is what I have so far. Okay, so I want to check to see if there is any y or z in it. So differentiate respect to the y. So f sub y. With respect to the y, this would be the drop down. So we get x squared z and derivative of the g respect to the y. But you have it in number 2. You have it in number 2 that f sub y is x squared z. Compare them together. These two would cancel out. So this is it. Your round g, round y would be 0. That's it, which is no good. So this means g of yz is constant. But remember, your constant can be a function of z. Okay, it's a constant, but the constant can be z. Okay, so the question is going to be how about z? So the function so far is so far the potential function should be x squared yz plus h of z. So question is going to be what is h of z? So you differentiate respect to the z, you compare it with the f sub z to see if there is anything in it, which is not going to be, but we have to check it. Any question? So if you differentiate respect to the z, that give x squared y, and the last part is just x squared y. So you can drop it down. So your potential function quickly would be x squared y z. Okay, but let me just show you. So we find you find the f sub z here. Okay, f sub z is going to be x squared y plus h prime of z. So from the equation number 3, you bring f sub z, which is x squared y. So you compare them together, these two would cancel out. We get h prime of z equal to 0. That will tell you that h of z is c, which is no good for you, because we are interested in one potential function. Okay, so the conclusion is going to be the potential function that I'm going to use is simply x squared yz. Okay, one potential function will be, even if you carry the c, the result is going to be unchanged. Okay, so that's it. This will tell us that the function is conservative. Okay, so I just explained it for you, just for your information. You know what's going on. So there you are, since f is conservative. Conservative, you know, by it follows, if you like, it follows that that the integral of fr dr, remember dot dr, or just the integral, is independent, is path independent, or is independent dependent of path, and by fundamental theorem of, okay, by the fundamental theorem of calculus or line integral. So in that case, f of r dot dr, if you like, or c is going to be just what is f of r of b, remember, minus f of r of a. But we just, as I told you, it's free. So I pick one of the C is going to be a straight line. When it's going to be a straight line, then this R of B is going to be simply the value of the function, which is endpoint. So the endpoint is 1, 2, 4, and the initial point is 1, 1, 1. Okay, I explained it that I can pick any C I like. So I pick a C that's going to be a straight line. If it's going to be a straight line, the initial point and would be the same, because this is just a linear line, if you like. Okay, so go to the function and find it. So this is your function. So f of 1, 2, 4 is 1 squared, 2, 4, which is 8. F of 1, 1, 1, which is 1. Okay, it's going to be just 1 squared, 1, 1, which is 1. So the integral in question is equal to the 7. So the integral of 2x, y, z. I just rewrite it, dx, x squared z dy plus x squared y dz is equal to the 8 minus 1, which is equal to the 7. Very nice method. Very nice, because you don't have the, you don't have the curve. You don't have the curve, but automatically you can find the integral. Okay, and that's a great deal to be able to do this type of ideas. How did I find out that f is conservative? Again, because I can find, I did find a potential function. You see, remember, it's conservative if it's going to be gradient of another function. I didn't have to check it. You see, I didn't have to check, okay, because I guess that it is potential. So a force is conservative if that force can be written as a gradient of a potential function. So I find the potential function. Since I find the potential function, so this means it's conservative, okay? I didn't check it. I didn't check it because I was sure that it is going to be potential, then I'll be able to do this integral, okay? So that's a great great problem, really. Just get to know it, that you just use two great facts. The first one, that your force is conservative, so your integral is independent of the paths. And the second part is you're using fundamental theorem of integral that will tell you that in that case, the integral is going to be just evaluation of the potential function at the endpoints. And since the endpoints are free, you just get exactly the same one. So these are going to be the endpoint, that A and the B that I identify over here. Okay. So, we give one of them because that's great. This is very good way to test those two great theorems that we did. Now, there is going to be a third one. I give you a break now. The next one is we want to find the line integral, but the function would be very difficult. So, and you know that you want to find the line integral on a closed curve. On a closed curve, and this function is not conservative. If it's not going to, you know that if the function is conservative, line integral over the closed curve are going to be 0 because it's independent of the paths. But if the function is not going to be conservative and you would like to find the line integral on the closed curves, then we can apply the Green's theorem. Okay. And the Green's theorem usually used when the integral is impossible to find. So we give you one and we give you the hint that apply the Green's theorem. So let's have the break. We come back. I give you a couple of them, so get the experience to see how to handle it. And then we finish the integral parts. Okay. So it's 15 minutes. I come back. I have 3 problems for you. They are not on that practice quiz. I didn't get time to add it, but I'll do it later. But I write it down for you because sometimes when it's not summer, we talk about the Green's theorem after the quiz 4. But since it's summer, okay, we push it if you like. So that's why you didn't see it on that. But it's nice. I'm giving you 3 nice problems. And 1 problem with the greens will be given on this quiz and 1 on the final. Okay, so see you in 15 minutes, 12:15. Okay, we are going to continue. Number 5 is very similar to this one. So, if I get time, I can talk about it, but otherwise, you will see the solution part of the final review. But the one that is missing, the case with the Green's theorem. Okay, so I'll give an example to see what we did wrong in test 2 and 3. No, the test 3, I haven't graded the test 3 yet. So the test 2, so if you have any question about it, you can, email me. The test 3, I will post the solution of the test 3 for you, not the test 2, because the test 3 is the one that we are going to cover for the final. If you have anything special, just let me know. Okay, I will pick up the tests after your lecture. I have to go to the campus. I take the test 3, I grade it, then I give you that's it. I give you the solution. If you want something specific about your paper, you just email me. You can join a Zoom meeting that I can show you, because we don't have any other sort of communication to take you, to give you that back to your paper. Okay, so let's get this case. So the cases that we did so far. So the integral was we have to do it straightforward. Then if if anything is provided, but the last one that we did, the difficulty was it's a very general question. So we were able to find the integral, although we didn't have the path, because that integral was independent of the paths. But the last case for this type of integration is the one that you have to apply Green's theorem. So you don't have this in your on the one that I posted. So I'm going to call it number 9. Then I add it to that, to the quiz that I posted. I didn't get time. So this is going to be the type, kind of the type 3 of these integrations. In this group, we want to use the Green's theorem. Okay, so we give you the instruction. So apply or use Green's theorem. We give you one of them on the quiz and one on the final. Use the Green theorems to evaluate each integral. Okay, each integral. Okay, so this is going to be the one. So you know that for the case of Green's theorem, your function is usually not going to be conservative. We talk about it. If you have a conservative force or a vector field, and if you want to integrate it along a closed curve, this integral is always 0. Done. But if the force is not going to be conservative in general, and you have a closed curve, and the function, of course, is going to be vector field in 2-dimensional, then you can apply Green's theorem to find it. If your function is going to be vector field in R3, then you have to wait. Then you have to go through the Stokes theorem to get it. Okay, so this is the idea of this Green's theorem. So the first one is this integral of x y squared dx plus very standard one, x dy. You want to find the c. We put this to just tell you that you're taking the integral on the closed curve. Okay, closed curve, and c is just a unit circle. Okay, so we would like to find this integral, if you like, along the unit circle. The unit circle C. Okay, there you are. Now, you know that for the Green's theorem, this is the formula that we have. Just remind you, solution. So just recall that the Green's theorem is going to be this one. Recall that by Green's theorem. Green's theorem any integral of this type on the closed curve, p dx plus q dy is going to be equal to the double integral. Okay, double integral on the domain of the t of the round q, round x minus round p, round y, and the dA, dx, dy, depends how we're going to write it down. Okay, so this is going to be the case, and this is going to be where you know that the boundary of this domain, if you like, is going to be C. So you have your domain. You see, this is going to be your domain that you have. Okay, anything inside and on this. So you are going to bond it. It's like a fence. Okay, so the inside is D and the outside is C. And the C is the boundary of the D. So if this is going to be the situation that we have, of course, your function must be, nice functions. It's a continuous, it's a continuous partial derivatives. Then you have to, you can use the Green's theorem. If your force is going to be, is going to be conservative, you know that in two-dimensional, in R2, when it's conservative, you compare the P and the Q together. So the round P, round Y is equal to the round Q, round X. So these two are equal to each other. This would be 0. And you know it. You know it from the past or from the theorem that if you integrate a conservative force on a closed interval, it would be 0, because for the conservative, the integral is the difference between, remember, difference between the value of the potential function on the end points of the curve. But this curve is closed. So the initial points and the terminal points are the same. So it cannot be used for the conservative force, okay? So there you are. You have the integral. So this means this is what you are going to do. So for the case that we have, okay, so we are going to check the P and the Q. So in this case, the C is the unit circle. Okay, C is the unit circle. So this is going to be your unit circle. Okay, this is going to be unit circle 1, 1, 1, 1. Okay, so this is going to be the C that you have. And you know the equation of the unit circle. Different format, we can write it down. You form the integral to see which format are you going to be interested in. If you are going to be interested in the Cartesian form, this is going to be in Cartesian form. Okay, and if you are going to be interested in the polar form, you know that then you can write it down in polar form. If you are going to be interested in polar form, you can go with the R of t, for example, to be equal to the cosine of the t and the sine of the t. Okay, when the t is going to be between 0 and 2 pi. So these are going to be two different formats, and then you're ready for it. So let's form this integral to see what we have. So according to the given one, this is going to be your P. So the P is going to be equal to the x y squared. So you need a round P, round Y. So we get the round P, round Y, which give you 2xy. Then you start with your Q. I'm sorry, your Q is X. Then you have to find the round Q. Okay, round Q, round X, which is equal to 1. So the difference is going to be, okay, the difference is, so we can write the integral. So by the Green's theorems, the given integral xy squared dx plus x dy over the C is going to be the double integral over that domain that we have. Okay, domain that you have a difference, okay, round Q, round X, which is going to be 1 minus 2xy. Then you integrate it respect to the A over here. Okay, so the domain that you're going to see there is going to be, the domain is going to be just the same as, you see the domain is going to be all the points inside and on the circle. This is your domain. So you have to decide how you're going to take this integral. You can, you better do it with the polar coordinate, polar form. Okay, polar form would be much easier. Otherwise, if you want to do it with the rectangular coordinate, it's possible. But it's hard because when you integrate it, you have to your x is going to be 0, 1, and the y is going to be semicircle to the top and the bottom. It's possible, but it's not advisable. So what we're going to do, we are going to change this integral into the polar form. So this is going to be equal to the integral in polar form, and this is the case. So your data is going to be between 0 and 2 pi, and your r, the radius is 1. So this is going to be your r. So change everything into the polar form. So this is it. We integrate respect to the r first, it's going to be 0 to 1. The integral respect to the data is going to be 0 and to 2 pi. Then you have to substitute for the value that you have. It's going to be 1 minus 2x. X is cosine of the data or cosine of the t. So that gives you cosine of the data. That would be the sine of the data. Okay, but remember there is an extra r for the polar coordinate. That is extra r. And then you go with the r, and then we go with the data. You see? So I change it to the polar coordinates. Any question? So integral respect to the r, which is easy, r squared over 2, so that gives me just a 1/2. So I'm going to the next page to continue. Okay. So I rewrite it again. I'm working on this integral. That is going to be 0 to 1, just writing down for myself. 2 cosine of theta, sine of the data. And this is r dr d data. So I'm going to continue. This is going to be 0 to 2 pi. Integrate respect to the r, so that gives me r squared over 2. Then everything else is the same. It's a 2 cosine sine. If you like, you can write down as a 1 minus sine of the 2 data. You don't have to, because when you want to integrate it, even you can integrate it as is. But it's a double angle. So the r going from 0 to 1. This is the data. So that gives you 1/2. Okay, so it's going to be 0 to 2 pi. And that is going to be 1/2 times 1 minus sine of the 2 data, d data. You can pull out the 1/2, so that's going to be 1/2, 0 to 2 pi. Okay, 0 to 2 pi. And 1 minus sine of the 2 data, d data. You can easily now integrate it. So that gives you 1/2. Integrate respect to the data, so that gives you data minus integral of a sine. Integral of a sine is going to be a negative cosine. So it's going to be negative cosine of the 2 data, but you have to divide it by 2 because of the u prime. And it's going to be evaluated from 0 to 2 pi. Okay. So this is going to be the case. And then what's the question? We substitute. When you change it, you see when you change the rectangular coordinate, polar coordinate, you see when you're integrating in the polar coordinate, you have to change the x and the y into what? Into the data. So what's going to be x? You're dealing with the unit circle. So in the unit circle, x is cosine of the t or data, and the y is sine of the t. So you have to substitute for everything else in the polar coordinates. Okay, you change the x and the y into the r and the data. So that is why I get the 2 sine, 2 cosine. Okay, continue. Let's simplify it. So this is it. We put the 2 pi and the 0 to get it. So there's going to be 1/2. I have a bracket. I use the 2 pi first. So that give me 2 pi plus cosine of, that's a 2 pi, 2 that I'll make it to the 4 pi. Okay, 4 pi over 2 minus, if you put the 0, so that gives you the 0 plus cosine of the 0 over 2. Okay, cosine of the 4 pi is like the cosine of the 0, and both of them are equal to 1. So this would be 1, and this would be 1. So the result's going to be 1/2 times 2 pi. Okay, 2 pi plus 1/2, and you get a negative 1/2. So that gives you 1/2 times 2 pi, which is pi. That's it. Nice. So the integral of x y squared dx plus x dy over c is equal to the pi. And then you're done. Any question? If you don't like it, you can do it directly. So directly means, you see, directly means you directly substitute. You see your equation of the curve is going to be, you have to write down in, okay, in rectangular form. Unit circle is x squared plus y squared equal to 1. Then it takes quite a while to do it. And if you say, oh, I can do it, I give another one, that would be impossible for you to do it. So it's nice to use the Green's theorem. Any question? So that is one version. You get to the, in a case of the unit circle, this is given to you. The other regions are usually a triangle or even a square. So I give you the second one as the problem that, you see, this was possible. If you don't like the Green's theorem, you'll be able to handle it, but not the next one. Okay, so that is part 1. Any question? Part 2, much more involved, is this one. So we want to find this integral. It's a very popular problem. Probably you may see it, in your assignment or the similar one. I want to find this is it. So this is a line integral on the closed curve. Now what's the function? You see, this is going to be the function. The function is e to the negative x squared, okay, plus y squared dx plus ln of y minus x squared dy. You see this integral? If you want to do it directly at the first step, you'll be in trouble, you see? You'll be in trouble to find integral of negative x squared dx. It's impossible. You cannot find it. You know that that's a normal distribution curve, distribution, if you like. When you want to find integral, you can only estimate it. So the direct method is almost impossible for this one, but the green is available. So what is C? This problem can be given on different curves, different path, but the path that I want to give you just to get the experience is a square. So we want to do it where C is going to be the boundary of this square. C is the square. We have some problems in your book. I don't want you to be surprised, so we have it. It's going to be a square with the following vertices. Okay. This is it, vertices. These are going to be the vertices of your square. And the point are 0, 0. Okay, 1, 1. 0, 0, 1, 1, 1, 2. 1, 2, and 0, 2. Remember, you're supposed to have a closed path, and this is going to be a very nice closed path. Okay, so get these points on the, locate them on the XY coordinate to see if your your region qualify for your Green's theorem. So solution, get these points. That's it. Locate the point. What do you have? 0, 0. This is going to be 0, 0. Oh, I'm sorry, it's not 0, 0. 0, 0 would be easy. I want to have it more exciting one. So, and let's have 0, 1. 0, 1, intentionally, I want to have this one. You have one with the 0, 0 in your book. Okay, let's see what is going to be now the case. Where is the 0, 1? And now 0, 1 is here. So this would be 0, 1. Okay, then we go to the 1, 1. So this is going to be 1 and this is 1. So this is going to be, so this is 0, this is 1. Okay, so 0, 1, 1, 1, then 1, 2. 1, 2, that is 2. So that's it. Okay, so that is, this is the 1, 1, and this is going to be 1, 2, then we get back to the 0, 2. And this is 0, 2. Okay, so the square is this one. Okay, this is going to be the domain that you're going to have. Okay, so as you can see, these are going to be the points that we have. So if you like, this is 0, 1, this is 1, 1, and this is 1, 2, and this is going to be 0, 2. So we have this view. Okay, so the point inside and around is the square. So the curve, you are going to be oriented on the counterclockwise. So the curve is this one. Start from this point. Okay, then you go up. Then this is it. So it is going to be a closed curve in the positively oriented. That's part of the argument for the theorem and the proof. Okay, so there you are. So the C is going to be the boundary. The C is going to be the boundary of, you see, the C is going to be the boundary of the domain that you have. And the domain that you have are going to be a collection of points. Okay, it's going to be a collection of points like X and the Y. You see, we can identify this domain. So if you want to identify your square, so you can say that my square is a collection of X comma Y with this restriction. So there's going to be restriction for your X. Your X is going to be between, okay, your X is going to be between 0, 1. So X is between 0 and 1. So X is going to be between 0 and 1. And your Y is going to be between 1 and 2. So Y is going to be between 1 and 2. Okay. So that gives you an idea, when you want to find it, to get this result. Okay, so it's qualified. It's qualified for the Green's theorem because, you have the function. Function is nice. It's partial derivatives can be found and they are going to be continuous. And the C is going to be a boundary. C is going to be boundary of the square. So we are able to apply the Green's theorem. Okay. So there you are. So by the Green's theorem, the integral is going to be, so let me just write it down once and just apply it. So by Green's theorem, this is it. So the given integral on the closed path of the C is e to the negative x squared plus y squared and dx plus ln of y minus x squared dy. Would we change the double integral? double integral on the domain that we already identified for you. Okay, and here is going to be round q round x minus round p round y, then the dA. And we identify that by p we mean this one. So that's going to be the p, and the by q we mean this one. Okay, any question? So go and form this part to see how we're going to handle the integral. So start with the p. P is equal to the e to the negative x squared plus y squared. So you have to differentiate respect to the y. So round p round y is going to be what? It's going to be just simply 2y. Then start with your q. Your q is ln y. You see the part that you were worrying about it would disappear. The part, e to the negative x squared ln y. So you want to find around the q around x. It's just simply negative 2x, you see? So you're just integrating what? Integrating the difference. The difference is going to be what? It's going to be negative 2x minus negative 2y. Okay, so we are going to continue. We say that, oh, we have to find this double integral. So the double integral over the d, and the round the q round x is negative 2x. Okay, negative 2x, then minus round p round y, which is going to be the 2y, and on the dA. So this is going to be the question. Okay. Now is a double integral in terms of x and the y, and the region is nicely given to you. You see x is between 0, 1, y is between 1 and 2. So it's kind of ordinary double integral. Okay, double integral on the rectangle with a constant limit of integration. So nothing to worry about. So it's going to be double integral. It doesn't matter which one goes first. You may go with the y first, it's going to be 1 to 2. Then you go with the x, which is going to be 0, 1. Okay, so the function is negative 2x minus 2y. And the way I write it down, I integrate respect to the y first, and I go with the x. Any question? So you see nicely, we shrink it. We remove all those trouble terms. Okay, the terms that make trouble for us. By the green theorem, then just integrate it. So this is it. It's going to be integral 0 to 1, integrate respect to the y. So that gives a negative 2xy minus, that gives you 2y squared over 2. It's going to be minus y squared. Okay, then you have to find it from y equal to the 1 to 2. And then when you're done, you come back and you do the dx. Okay, to get this. So go on, substitute, then integrate respect to the x. So it's going to be equal to the 0 to 1. Okay, 0 to 1 minus 2xy, y equal to 2. So y equal to 2, that gives you 2 times 2, 4, that gives you 4x. Minus, if you replace y by 2, that gives you 4. That's when you put the y equal to 2. It's going to be minus when you put y equal to 1. Okay, y equal to 1, that gives you negative 2x minus 1. And then everything dx. Okay. Then continue to get this one. So I'm going to just simplify it a little bit. It's going to be 0 to 1. So I have a negative 4x minus 4. So that gives me a positive 2x and a positive 1 and dx. So again, it's going to be 0 to 1. The x is negative 2x and the 2x that gives me negative 2x. And the negative 4 plus 1 would be negative 3 and dx. Now integrate respect to the x. So that gives me negative 2x squared over 2. It's going to be negative x squared. Okay, minus 3x to be evaluated from 0 to 1. If you put the 1, that gives you negative 1 minus 3, which is the negative 4. Negative 1 minus 3, the rest would be 0. Minus 0, which is equal to -4, the final answer. Very nice integral, you see. As I told you, the other one, you may be able to do it without the Green's theorem, but this one is impossible. I mean, you can't do it by just finding those integrals, and the integrals involved are very, very difficult. So this is the power of the Green's theorem, really, and the way you are going to use it. So most of the integral can be done by other method, but you can put anything complicated you like. It doesn't matter. As soon as you go to the round Q, round X, everything would be nicely done. Okay, so this is it. Let's give you two different ones so that you can see it. I have another one. I can write it down, but you do it yourself. It's easy because the area here is rectangle, a square. You may have a triangle. I think the other one is a problem in your book. Any question? So just give you better understanding of the Green's theorem. Again, I told you, if you want to take advanced calculus or the calculus of a complex function of a complex variables, you need the Green's theorem to be able to, of course, they use Green's theorem to create a new formula for their integrations. But that would be important to know. Okay, so I just write this last one for you, but you can do it yourself. It's not difficult, or I can give you a little bit so you can do it. So this is it. The integral is this one. I think this is in your book. I don't remember. E to the 2x plus y. Okay, dx plus e to the negative y, dy. And on the c, of course, this is c is closed. What is c? C is the area, is the boundary of a triangle this time. Okay, where c is the boundary, or c is the triangle. Okay, it's going to be a triangle or triangular region, if you like, with the vertices, the vertices are going to be 0, 0. I think that's the origin. That's easy to handle. 1, 0, and 1, 1. Okay, that's going to be the one. Of course, these functions are easy. You can do it if you want to do it straight or right on. It's possible. But we want to just check the Green's theorem. Okay, so check the region that you have to see if it's qualified. So get this triangle. So you have your triangle. This is going to be 0. So you go to the 1, 0. This is 1, and you go with the 1, 1. So this is going to be a triangle that you have. Okay, so easy to handle. So that would be your domain. But this is going to be the path, C, start from here. So this is going to be the C. So you have the C here, and the domain is going to be anything inside and the boundary. This is going to be your domain. Okay. So it's nicely qualified. C is closed, the functions are nice. So we can use so you have to identify your domain that you have for the integration of a second part. So yes, you know that for the integration, you can say that the domain is going to be, again, it's a collection of points. You see, you can fix the x. Your x is going to be between 0 and 1. And your y, of course, you know that you can consider this one as a type 1 region. So y goes, up, down, up, down, up, down. So it's going to be down, start with the 0, y. But the up is going to be the line, y equal to the x. So this is going to be your domain now. It's a type 1 region. It's a type 1 region because they're all 1, 1, 1, 1. So the slope is 1. So that's it. So your integral according to the Green's theorem. So by, again, by the Green's theorem, this is what you're going to have. You're going to have the integral e to the 2x plus y dx, okay, plus e to the negative y dy over the c. So this is going to be a double integral on the domain D, and this is going to be around Q, around okay, around X minus around P, around the Y, and then the dA. And you already decided what are you going to have. So this is going to be your P, and this is going to be your Q. Okay, and it's very easy to find these integrals this time. So your P function is this one, e to the 2x plus y. So you want to find the round P, round y. You know that the exponential function never change. It's going to be e to the 2x plus y, and you differentiate the top respect to the y, that give you 1. So this is simply e to the 2x plus y. Okay, because you differentiate respect to the y. And your q is going to be e to the negative y. So round q round x is simply 0. Okay, so the difference is very easy function to integrate. Okay, so the double integral that you did have, okay, the double integral on the D, and the difference are going to be simply 0 minus e to the 2x plus y. Okay, on the dA. This is it. And you already decided how we're going to, you have the domains of 0 to 1, and then 0 to x, and the function is simply negative 2x plus y. Then you just respect to the y and then respect to the x. You see, easily can be done. So, you know, exponential function never change. So this is 0 to 1. You just simply say, get the same function, e to the 2x plus y, and your y going from 0 to x, and then when you're done, you integrate respect to the x. If you substitute, give it two nice number or easy number. If you put the x, so that gives you 0 to 1. Okay, you can pull out this negative sign. That give you e to the, if you put the y equal to the x, that 2x and x would be 3x. Minus, if you put the y equal to the 0, if you put the y equal to the 0, that give you e to the 2x and the dx. You see, that's right. Any question? You just integrate respect to the x, and then you're done. So it's going to be minus integral respect to the x, derivative is going to be e to the 3x over 3, the first one, e to the 2x over 2, the second one, going from 0 to 1. Okay, you know, the result, you can use your calculator or just give us the answer. Is going to be negative. So if you put the 1, so that give you e cubed over 3 minus e squared over 2 minus, okay, and this is it. If you put the zeros, that give you 1/3 minus 1/2. So the final answer would be something like negative e cubed over 3 minus e squared over 2. And over here, negative would be positive. So it's going to be positive. And this is going to be simply, okay, it's going to be 1/3 minus 9/3 minus 1/2. So the common denominator would be 6. Okay, that give you negative 1/6. So we can simplify it. Give us we can find the common denominator of all of them to put them together as a 6, or just write it down. You know, we can check it yourself. So just to see how how you handle it, different formats of the Green's theorem. Okay, because we didn't have enough practice on this one, because on the final review you have only one. But this is better. Let's see when you are done with your quiz. Then there is another one. I put that one in your quiz so that you practice, so that you have all of them really to get the idea. Okay, that's a Green's theorem and all those integrations that you have to do. And number 5 is, you can check the final review. You will see the solution of the 5, and solution of all of them really is over there, because I put them as a final part, but you don't have those Green's theorem that I give you here. Okay, the rest of the problem are just we just checking some okay, we're just talking about these the formulas that we have. You see the curl and the diversion, etc. They are just a straightforward problem, and we are mainly interested in this, but we give you one of them on this quiz, but not on the final. I just give you one of them just to know it, but otherwise it's not our concern. Okay, any question? So read this integration really carefully, because you have to get practice. It takes time, some of them. So if you practice in advance, you see, you know it, you can do it quickly right away. So for example, number 6 is straightforward. A function is given, then they ask you to find the gradient. Okay, it's not a big deal. So I just remind you that for number 6, the function is, they ask you to find, you see, that's it, find, that's a number 6, find the divisions. Okay, division, div of the gradient of this function, e to the x plus y plus c. It's a divergence of the, okay, of the gradient of the function. So you find the gradient first. It's like a composition of 2 functions. So we go with the first one first. The gradient, you know that it's going to be the partial derivatives. So the solution is going to be, so you're going to call this one a function, f of x, y, z, and it's x plus y plus z. Okay, so the gradient of this function is going to be simply the partial derivatives. That's it. Easy to find. Exponential function never change, so everything is going to be the same because u prime is 1. So that gives you e to the x plus y plus z, e to the x plus y plus z, and e to the x plus y plus z. That is the gradient. Okay. So it's a new function. The divergence of a function, you know that divergence of a function is a scalar. It's a scalar valued function, and that would be just, you see, recall that. Recall that if you want to find the divergence of a, okay, for example, if you want to find the divergence of function g, is going to be simply rond g rond x plus rond g rond y plus rond g rond z. That's it. Is a scalar valued function. So your function is this one. So that's it. So this would give you what? So it's going to be equal to the rond x of the function e x plus y plus z. They are all the same. Rond y e to the x plus y plus z, and the rond z e to the x plus y plus z. Just make sure you have the formulas available, otherwise it's not a big deal. So it's going to be the same thing, x plus y plus z, because exponential function never change, okay, and u prime is 1. So all of them are going to be the same. That's it. So the result is going to be 3 times of the E, X, Y, Z. So this is the divergence of the, okay, gradient of that function that you were interested in. Okay, it's going to be because that was the section that we did, and we want to confirm it. Okay, that's a number 6. Number 7 is something that's, we prove it as a theorem, but they ask you to confirm it. Okay, number 7, I proved this one during the lecture. I can remind you that as well, you see. So they ask you to prove. Prove that the divergence, okay, divergence of the curl of any vector field function is equal to the 0. Okay, I proved this one. So this is going to be for any vector field f, of course, with the continuous partial derivatives. With continuous, okay, partial derivatives. So again, you have to have the formulas to be able to do it. You need the formula for the curl. So the solution is going to be, you cannot pick any special function. Your function must be a general one. So you're going to suppose a vector field in R3 in general. So your vector field is going to be this function, f of x, y, z, no specific example. So start with your function m, say m times I, n times j, as r times k. When the m and r are function, real valued function of the 3 variables, and again find the curl. Okay, then find what is going to be now the curl of the vector value function. Remember, the curl is going to be the del cross f. It's a vector function. It's going to be the cross product of these two functions. And the cross product means that's it. You are going to have the I, j, k. The first row is going to be just the differentiation operator, round x, round y, round z. And this is your functions, which are going to be m, n, and a. That's it. So that was the formula for the curl that you have it in on your lecture notes. So you find this one first, and then you have to find the divergence, which is going to be just the second derivative. Okay, so we extend it. You know that the first row, second column, this is it. So I'm going to write it down for you when the extension, then in order to get the divergence, so you have to differentiate it again, like the formula that I gave you. See, that's the formula. So you find the derivative of the components of that vector, you add them together, and you show that they are going to be equal to 0. So the determinant of this matrix is the following. Okay, so if you do that, so the curl of f, again, you have the formula, you can do it right away. So we compare those 3 together. I compare the p and the n. So this is going to be round p round y minus round n round x. That is the first part, times I minus, then I compare the p and the m. So round p round x minus the round m round z. Okay, did I use the p or r? Oh, I used the r. It doesn't matter. We can change this into the r. R, R. Then I have to compare the other two, M and N together. So it's going to be round N, round X minus the round M, round Y. So that's a J, and this is the K. See, that's your K. So for the divisions, okay. So for the divisions, you have to remember is going to, I'll just remind you again that the divergence of a function G is just a round G, round X plus a round G, round Y plus the round G, round Z. So this is going to be your function. So operate. So the curl of the divergence of the divergence of the curl of the F is equal to partial derivative of the first one respect to the X. Okay, partial derivative of the first one respect. I write it down. So partial derivative of this round R round Y minus round N round X. Okay, plus, remember it's a scalar valued function, no IIG. So the partial derivative with respect to the Y of the second one, there is a negative sign here. So I apply the negative inside. So it's going to be negative round R round X plus round M round Z. Then the partial derivative with respect to the Z and the tail one. So that gives a round N round X minus round M round Y. Okay, so the partial derivatives of each component, I put the N negative sign inside. Now apply the partial derivatives. The first one is going to be round 2 of R round X round Y minus round 2 of N round X square, if you like, because that's the X and the X. Okay, the second one is going to be minus round 2. It's going to be round 2 of R, but the round Y round X, and that's going to be plus round 2 of M round Y round Z. Okay, this is going to be the case. That was excellent. You know the last one. The last one is going to be round 2 of N over the round Z round X minus round 2 of M over the round Z round Y. Probably I missed something over here. So I differentiate respect to the X, so that give me XY. And sorry, that was the P. So this must be a Z. Okay, because this is R and N. R is the last one, the Z and the Y. So this is round Z. That would be round Z, and this is round Z. So I'm going to have round X, round Z here, because all of them must be cancelled out. Now they are ready. Round 2 are, and this is it. These two are going to be cancelled out because the order is not important, because we have a partial continuous partial derivatives. So round 2n and the round 2n, again, the order is not important, zy. So these two would be cancelled out. And the last two are going to be, I'm sorry, these two would cancel out. Then the last one would cancel out too. So it would be 0. So, we just proved that the divergence of the curl, okay, of any vector field is equal to this. It's a theorem in your book. Just wanted to see, how you operate with these type of problems. Okay, so that's a number 7. In number 8, they give you a function and they ask you to check this one. So you find it and you integrate it. This is number 8. Yeah, the number 8, I just do the quickly the 8 to finish everything. Then we give you one question and we ask you to evaluate this. So the number 8, the last one, is if you have a vector field, you can talk about quite a lot about these type of relations. If it's going to be just a kind of vector calculus or advanced calculus, they do quite a lot, or sometimes in physics. Because when they are going to be a specific force, then this operation means something. So they have something for it. It can also be used in geometry. Okay, so what's the question? The question is they ask you to show this one. We wanted to show that. Remember, this is a vector dot the curl. The curl is also a vector. We want to prove that in this case, this product is equal to 0. Okay. This is it. So it's a straightforward problem. You find the curl, you already got the formula for it, and then you just multiply dot product with the f and show that this is going to be equal to the f. Okay, so not a big deal. So you already got the formula for the curl here. You can substitute or you can find it yourself. So solution, this is it. So we start with the function and we label it. So the function is x, y, z, which is the y squared, z squared, x squared, z squared, and the x squared, y squared. So label it as usual as, I want to use that formula. So I'm going to label it M, N, P or R, doesn't matter. I go with the R here, so I call it R. Then write the curl. Okay, so this is it. And the curl of F. You can write it down in the, in a matrix form if you like to find it, or just use that formula. So you have 2 different options to do it. Okay, so one option is with the matrix, or the other option, if you go to the matrix, this is it, easier. This is I, J, K. Then differentiate with respect to the X, differentiate with respect to the Y, and the differentiate with respect to the Z, the function. The first one is y squared, z squared. The second one is x squared, z squared. And this is going to be x squared, y squared. See? As you move on and you differentiate, that would be easier. Okay, so this is it. It's going to be equal to the I times, or just use the formula. This is it. Derivative with respect to the y minus derivative with respect to the z. Derivative with respect to the y over here is going to be 2x squared y minus derivative with respect to the z would be 2x squared z. That's the first one. Okay. Next, minus j times, eliminate the first row, the second column. Again, derivative with respect to the x, 2x y squared minus derivative with respect to the z, 2 y squared z. That's a g part. Okay, plus k part is going to be k times derivative with respect to the x, 2x z squared minus derivative with respect to the y, 2y z squared. That's it. It's the best way, to write the curl. Now, dot product with the function. Dot product with the function is going to be f dot curl. you know that the dot product is going to be just a number. So you're not going to have the ijk, you just simply multiply these together. Okay, so this is going to be the case. So for the first part, you get y squared, z squared times 2x squared y minus 2x squared z. That's the first one. Second one, there's a negative here, so we go with the negative. Second component here is x squared z squared times it by 2x y squared minus 2y squared z. That's the second component. And third one, it's x squared y squared times it by 2x z squared minus 2y z squared. Okay, if you multiply them together, it would be 0. Well, if you want to see it, multiply, that give you 2x squared y cubed z squared. That's the first one. Next one is going to be minus 2x squared y squared z cubed. This one minus 2x cubed y squared z squared. Okay, this one negative would be positive, positive 2x squared y squared z cubed. And the last one, that give you 2x cubed y squared z squared. And finally, minus 2x squared y cubed z squared. Check to see if you haven't missed anything. Ooh. So x squared y cubed z squared. X squared, that's it. X squared, no. That's the last part. That's it. These two are the same. So that would be cancelled out. Next, x squared y squared z, x squared y squared z cubed. So these two would be cancelled out, and eventually the last one are going to be the same. So yes, it is equal to the 0. Okay, so this is the way, you just want to give you, just put these formulas together really to get the ideas. Okay, so we give you one, it's a straightforward problem because everything it would be given to you for the specific case. So that's it. Focus, study this one carefully. As I told you, it's good for you because this is 6 questions on the final. Especially make sure you understand the notion of the line integral, really, those integral that I did, focus on those. And then I post a quiz later tonight. Then do it, we bring back, we can talk about it again, but surface integral, that's the one that we need. I post your last extra points is going to be all line integral and the surface integral. I want to give you more idea, okay, more practice really. So I'll have to set it up during this weekend. I just post it for you because I don't usually give anything for the final, but I don't mind because we wanted to practice and get another 5 points in case, in case you need it. So just get that one also done. Okay, and that's it. So have a good one, and I'll pick up your test. I try to post I will grade it, and I post the solution of test 3 because test 3 is important. So you compare it, if you miss anything, you will see it. After I grade it, then I can drop your lowest test and be ready for the final. And that's it. Just you're almost done, but we need to take a final. Remember, you already got all the hundreds, but you have to have a good one on the final, and you are going to have it. No problem. Okay, have a good one. Take care. Bye-bye.